Okay, so welcome everyone officially to this sold out webinar from Mitchell Provan, which is hosted by the Great Lakes Nature-Based Coastal Solutions Community of Practice. As usual, I have a few points to cover before we jump into the main talk today. The Great Lakes chapter acknowledges the diversity of Indigenous peoples within the land that we now call Canada and values the historical and contemporary contributions of these people in the regions where we work. In particular, we recognize the importance of Indigenous ways of knowing to our understanding of the natural world. We encourage you to reflect on where you live and work and how we can contribute to reconciliation. Now, as many of you know, this community of practice was established by the Coastal Zone Canada Association, who also put on the Coastal Zone Canada Conference every 2 years. And the next Coastal Zone Canada Conference is coming up very quickly. It's being held in Charlottetown, PEI, June 9th through 11th of next year. Abstract submission is open, and we're really excited to have a presence from our Great Lakes COP at the conference next year. Members of the executive committee will be in attendance, and we're planning on hosting a panel discussion on the challenges and barriers for implementing nature-based coastal solutions. Maybe I'll ask one of our exec members to just share the link for the conference in the chat so everyone can see if they are interested. And let us know if you think you'll be attending the conference. I know there are a few early career professional grants available, which you can see on the conference website, if that's of interest to you at all. It'll be great to know if anyone else from the community is attending, so do let us know if you think you'll be able to go. Now, not wanting to take too much time from the main talk today, I'm going to introduce Mitchel Provan from the National Research Council Canada. And then following the presentation, we do have time for questions. So feel free to add your questions into the chat and we can ask, or raise your hand during the Q&A and I can call on you to ask directly. So Mitch's talk today will focus on the increasing interest in exploring nature-based solutions as alternatives or complements to traditional hard infrastructure in coastal environments. While coastal nature-based solutions have been used for many years, there remains a significant need for data to support their design and implementation. Physical modeling serves as a powerful tool to simulate and assess nature-based solutions in controlled environments, offering valuable insights that can be used to develop design equations, refine approaches, and optimize solutions before they're applied in practice. This presentation will introduce the concept of physical modeling, its role in studying coastal nature-based solutions, and examples of past nature-based solutions. And with that, Mitch, I will pass it over to you.
Sounds good, thanks. I'll share the screen here. Okay, so yeah, thanks for attending, everyone. My presentation today is going to be on using physical modeling as a tool to study, optimize, and de-risk coastal nature-based solutions. So nature-based solutions are strategies or measures that depend on or mimic natural system processes to provide flood and erosion risk management function, while also delivering environmental and other societal co-benefits. And the benefits of nature-based solutions are starting to receive increasing attention. However, these solutions remain comparatively underutilized compared to more kind of classical engineered approaches or designs. There are a number of barriers to the broader uptake of nature-based solutions, coastal nature-based solutions, and these include challenges in predicting performance compared to the alternatives, limited design guidance compared to traditional engineered solutions, challenges in the evaluation of benefits and economic appraisal, a lack of institutional, financial, and regulatory capacity to strategize, implement, and monitor nature-based solutions. Also, a lack of awareness of the role nature-based solutions can play in supporting social and economic resilience, and others. Where physical modeling can help is these first two. Physical modeling can help with these challenges of predicting the performance, and as well as the limited design guidance compared to more traditional solutions. Physical modeling, for anyone who may not be aware, it's a tool that we use to simulate the behavior of water in order to study hydraulic processes and interactions in a controlled environment. This is typically done through scaled model representations of the system that's being modeled. However, some models are also conducted at full scale in certain circumstances. It provides a hands-on practical approach to develop effective engineering designs and conduct applied research. And physical modeling is also a key tool for assessing unique and complex problems. So kind of the examples I show here are kind of more classic physical model applications. This is looking at a large offshore breakwater structure and its stability under large wave attack. This is looking at a beach and the mobility of the beach and reshaping of the beach under a variety of storm waves with a little model truck to show the scale. And this is a large port development down in South America where they're looking to expand their port facilities and looking at moored ship motions as well as stability as a breakwater here. So these are kind of more traditional approaches to physical modeling and coastal engineering, but I'll show a number of examples of kind of approaches that include or incorporate nature-based solutions. In coastal engineering physical models, there's two primary types of facilities that are used, flumes and basins. So flumes that are shown pictured here on the left are typically long, narrow facilities that are used to test sections of an object or structure in a two-dimensional environment. Since only a section of the structure or whatever is being tested is done, you can typically achieve larger model scales, including up to full scale, depending on the project and the facility, which is very useful for nature-based solutions. However, flumes are not able to represent 3D effects, which includes, wave transformation processes such as refraction and diffraction, oblique wave attack, longshore processes, and other things like that. Basins, which you can kind of see just a portion of one pictured on the right here, are larger square or rectangular facilities that can accommodate models of complete structures and shorelines. It allows for accurate representation of the shallow water wave transformations, oblique wave processes, and longshore currents. However, the models typically need to be conducted at a reduced scale, which ranges from about 1 in 20 to a 1 in 100. So just to make sure everyone's on the same page, when I talk about a model scale of 1 in 20, that means all lengths in the scale are reduced by a factor of 20. So an example of using physical modeling as a tool, physical modeling as a tool to study. Since the modeling is conducted in a controlled environment, it's a great way to study and understand the performance and behavior of a variety of nature-based solutions. Hydraulic conditions, such as the water levels and waves, can be easily changed in a model, and the performance of the nature-based solution that's being tested can be studied under a variety of conditions. Extreme events can be generated, and models can be tested to failure at no financial risk. In a physical model, you typically want to test to failure as you find kind of the upper bound of the ability of whatever is being studied. Whereas, if you construct something in the field, even as a pilot study, you really don't want failure as it can be quite expensive to rebuild or repair. And it's also much easier to measure data in a physical model and change the measurement locations based on observations. Very quick to change the location of, your instrumentation in the model. And you can do it in between tests and rerun the same test if you see you're not capturing that data. Whereas in the field, it's very difficult, if not impossible, to change the location of instrumentation during a large storm event because you don't want to be out there in the waters during a large event. So an example of using physical modeling as a tool to study is a study that we did here using coastal vegetation. So living shorelines are the most recommended nature-based solution strategy for low to moderate wave energy settings. They can help reduce the risk of flood and erosion in coastal areas through both an increased bed elevations as well as providing resistance against the wave propagation. Now, there's been a lot of studies on coastal vegetation, a lot of experimental studies done. However, the majority of these studies have focused on the wave attenuation abilities of mature and dense vegetation. However, there's a knowledge gap on the ability for immature or low density marshes during the earlier stage of marsh restoration or construction and kind of their ability to attenuate wave energy. And so we conducted a series of full-scale flume tests using live plant specimens that are native more to the Atlantic Oceans here in Canada, but the similar study methodology can be carried out, and we have plans to carry it out for other plant species. Just down here is just a sketch of the testing setup. So the waves approach from left to right. We install, a slope and grade here, and then a flat floor out in front. We had our experimental marsh, our model marsh installed in here with a number of wave measurement locations throughout to investigate the wave attenuation as the waves propagate through the model marsh. Here's some photos. So we obtained the plants from a local nursery or somewhat local nursery. We tested two different types of densities, the lower density ones you can see here and the higher density you can see up here. And we installed these plants in milk crates, so we're able to keep them alive outside until they reached a size that we wanted to test. And they were then easily transfer them into our flume and install them in the flume. You can see there was also we put a fine layer of gravel on top of the soil in the plants in order to reduce or mitigate the chance of erosion happening during the test, just to keep everything the same from test to test. As I mentioned, two plant densities were studied. One was the lower density was 36 stems per meter squared, and the higher density was 81 stems per meter squared. We tested both regular and irregular wave conditions with wave heights ranging from 10 to 30 centimeters. Peak wave periods ranging from 2.25 and 3.25 seconds, and then water depths of 30, 60, and 90 centimeters. We also investigated the interaction of waves and currents and the ability of the plants to attenuate wave energy. And so we tested with currents at 0.25 and 0.5 meters per second. Just a little video clip, nice clip showing the vegetation moving underneath the wave action, and just a few other photographs of the test in progress. I'm not going to go into a deep dive into the details of the results because there's just not enough time for it. So if you're interested, my colleagues did publish a paper that has a more kind of detailed explanation of the results and the studies that were found through this physical model. Just kind of quickly looking at some high-level results. These two plots here are plotting the distance along the marsh, which is shown in green here, and then essentially the wave attenuation or the transmission coefficient along the y-axis, both for no vegetation in purple, the low density vegetation in the blue squares, and the high density vegetation in the green triangles. And that was done for an emergent case where the water level was only 30 centimeters, and then for a deeply submerged case where the water level was 90 centimeters. So you can see, as you might expect, there's a clear impact of water level and submergence on the ability for the vegetation to attenuate the wave energy. Also looking at the influence of wave period on the transmission coefficient and the influence of currents as well. Again, anyone interested, I'd recommend taking a quick look at this conference paper that was published. So looking at physical modeling as a tool to optimize. So experimental tests or physical modeling allows for changes to the design of a shoreline protection scheme or any sort of structure, including layout, size, type of protection, among any other factors. You can make these changes relatively easily. Now, the interaction of waves with the coastal structure is a very complex process and can be difficult to accurately model these numerically, and design equations may not provide an optimized solution. So, classic engineering design equations will give you, they're based off of usually physical model tests, the majority of them, but they're kind of more for general cases, where once you start designing structures in coastal environments, certain details in the bathymetry and the interactions of the waves with the shoreline and other structures and stuff, it can all change the kind of the optimum solution that can be found through design equations. It also provides the opportunity to reduce structure armor size and extent, and this allows to find construction cost reductions and/or incorporate more nature-based solutions into the design. So an example of using physical modeling as a tool to optimize here that we've done is for the Jim Tovey Lakeview Conservation Area, which is a shoreline of eastern Mississauga and Lake Ontario, and it had a degraded quality of terrestrial and aquatic habitat due to current and past land use utilization. The goal of this project, of the larger project that we conducted the physical modeling study for, was to create a new natural park that both establish ecological habitat and public linkages, and as well as an innovative use of clean fill from regional infrastructure projects. I just wanted to note this was a joint project from the Credit Valley Conservation, the Region of Peel, and the Toronto Region Conservation Authority. There was 5 alternative designs, which 4 of them included kind of the headland bay configurations that you see here. And the preferred alternative that we tested and kind of helped optimize in the physical modeling study was called Island Beach C, which is, you can kind of see a schematic of it here. This alternative included about 1.5 million meter cubed of fill, a headland with an armor stone revetment around it, which is outlined in red, about 1 kilometers of cobble beaches, which you can see in yellow here, 3 offshore islands with the blue arrows on them, a terminal groin at the end to kind of anchor that cobble beach, and as well as 2 creek outlets with the green arrows here. And so in order to support the design of this, 1 to 35 scale physical model was conducted in NRC's large area basin I just want to note that this was done in partnership with Shore Plan Engineering, who are the design engineers for this project. The physical model was used to verify the stability and response of the headland beach system under a range of wave conditions, and as well as optimize the project design elements, including the beach fill and rubble mound structures. I just have a schematic of the shoreline here, and you can kind of see a similar view from the physical model matching up nicely with the schematic. It's just a number of photos from getting the physical model built, including, so we represent all the bathymetries typically out of concrete, because it gives us a hard, stable surface to work off of that remains unchanged in between tests, so you can directly compare one test to another. So we have our technicians, working hard, pouring or placing the concrete and then finishing it. This is the wave calibration. So prior to any kind of physical modeling study, before you actually start building the structures and testing them, you do a series of wave calibrations where you make sure that your wave machine is producing the waves that you want. And so that's done before any of the coastal structures are constructed. Here's the technicians building that kind of long cobble beach along here, finishing it off, and then building these kind of more offshore rubble mound structures, and as well as the revetment. One thing that we try to do in the physical model is to replicate as closely as we can the construction methods behind the offshore structures to ensure that the interlocking between stones is somewhat similar between the model and real life. So things like the cobble revetment and stuff, that's all shovel placed, because when you construct it in the real world, you have a big excavator or backhoe or something placing that material. All the actual armor stone is hand placed stone by stone. So we don't just shovel it into place. We place it one stone at a time to get similar interlocking between the stones that you would see when it's constructed in the real world. Just a few kind of photos from before and after testing and during. And again, I won't get into kind of the specific results here, but there is a paper published by my colleague Scott Baker with the information up here in the top right. Over here is just a nice shot of the waves interacting with the shoreline scheme here with the various islands and the different beach cells. And then the physical model was used to investigate the performance of it and provide some abilities to optimize it. So this is at the end of one of the revetments. You can see a bit of a scour hole forming here. And so that was altered in the next kind of design step and retested to ensure that, something can be done to eliminate that scour hole. Looking at erosion and deposition trends of the cobble beach, seeing, making sure it's eroding where kind of the designers want it to erode and accreting where they wanted it to. The reshaping of the cobble beach and the profile that it takes on. And then interaction of the waves with these kind of more offshore rubble mound structures. The study itself generated a large quantity of data used by the design engineers to further optimize and finalize the design plans. And then optimizations were achieved through the physical modeling study, and they led to significant cost savings for the overall project. Compared to the EA cost assessment, there's savings of approximately $3 million, which is more than 10 times the physical model study cost. So while physical modeling can be fairly expensive to undertake for a project, it can definitely pay for itself many times over through optimizations. This is my colleague Scott Baker working on the model here. This was a study that he was running. I believe a lot of the cost optimizations came through a reduction in the crest elevation of these structures, allowing to use less material, and then kind of leading to some of those cost savings. Another example, and this one's not yet happened, so I don't have any nice model pictures to show from this one, but this is for the Hillman Marsh on Lake Erie. This is an upcoming model study we'll have starting next spring. So we're excited to undertake this one with Seth Logan at SJL Engineering. The Hillman Marsh is located on the eastern side of Pili Peninsula, and it's a provincially significant wetland. It's historically featured a protective barrier beach over 1.5 kilometers long, which would shield the marsh from the potentially large waves of Lake Erie. A breach occurred in 2017. Here's an aerial photograph from 2017. You can see that breach here in the barrier island. And it rapidly expanded in the following years due to high lake water levels, increased wave exposure due to vertical downcutting, and obstructions to the natural longshore sediment transport. So you can see that breach initially formed 2017. 2 years later, it's widened. Another year, it's really broken open. And by 2022, you have a large breach in the island this big sand spit that's developed and kind of starting to encroach in the wetland behind it. And could potentially cause a lot of issues with wave-induced flooding to the lands inside that marsh if it's fully exposed to the potentially large waves of Lake Erie. So the design work is currently underway with preliminary designs, including gray-green approach with a combination of new barrier beach, buried rock berms, submerged rock shoals, and new fish habitat. This is just a schematic provided by Seth Logan. And this isn't the final design. This is just a preliminary design to show some concepts that could be included in the overall kind of rehabilitation project. And we'll be looking to test once there's the designs are further along and ready. We'll be ready to test it in spring 2025 to support the optimization of the coastal features and confirm that the final design will deliver the desired levels of performance. And the third one here, using physical modeling as a tool to de-risk. Physical modeling provides the opportunity to reduce project risk before construction. It allows to investigate the stability of various design elements and protection of critical infrastructure, and can also, in some circumstances, investigate potential maintenance-related issues and reduce the risk of expensive future maintenance of a coastal infrastructure project. So one example of that here is the Morgan Shoal dynamic revetment. Historically high water levels on Lake Michigan in 2020 resulted in wave-induced damage and localized flooding along portions of the Chicago waterfront, including South Lake Shore Drive. You can see a nice photo of it here. Here's the large waves kind of crashing against the shoreline of Lake Michigan near Chicago, starting to overtop the structures, causing some flooding along this pedestrian pathway. And you can see the cars driving along that South Lake Shore Drive, not too far inland from where the flooding is starting here. And some post-storm damage. Here's that same little shed or hut there. You can see, it's damaged the pathway. It's thrown up a lot of, larger materials onto the path and damaged a lot of these kind of placed armor stones or armor blocks, I guess, along the shoreline here. So the city of Chicago wanted to upgrade the shoreline protection near Morgan Shoal, both to increase the resistance of the shoreline to erosion, as well as increase the resistance to large wave overtopping events. The preferred design was to use a dynamic cobble revetment or beach to provide a more natural approach and allow for better public access to the waterfront. Right now, the access to the waterfront is not great with these large kind of blocks here, and they're looking to improve that for the public use. The initial designs for the dynamic revetment were conducted using numerical models and equations. However, in order to gain a better understanding of the complex wave interactions with the dynamic revetment, we conducted a large 1 to 10 scale physical modeling study in our large wave flume. And the main focus was reducing overtopping and potential future maintenance of the dynamic revetment. So a few photos of the kind of post-construction and pre-testing. So you can see those large blocks they wanted to repurpose, that people will be able to access this kind of nice, larger dynamic revetment or cobble beach on. And it's just another photo of a different model setup for the same project. It's important to do these type of studies at a large scale. So 1 to 10 is fairly large, especially compared to the 1 in 35 of the previous project we just looked at. Mainly because a lot of these dynamic revetments like to use rounded material. And they're mainly because it's nicer for people to walk on compared to normal crushed stone or angular material. And this rounded material, you can only get it so small. So in order to get similar kind of material interactions and sediment transport, you want to use a similar type of material in the model as you would have in the real world. And so you can see this kind of nice rounded material that we're able to get that was appropriately scaled and hopefully provide a very good representation of how the dynamic revetment would actually perform under the tested conditions. So we ran quite a few designs through a large range of wave and water level conditions, and the physical model study was able to help reduce potential maintenance costs, mainly post-storm reshaping of the dynamic revetment. So on the right here, I have a plot. This is basically distance offshore of the revetment, starting from the land side to the offshore side, wave directions from right to left, and then you have elevation on the y-axis. And you can see we did a number of test series here. I measured the profile and the reshaping. And so, initially we're getting these large kind of berm formations where the initial kind of crest of the structure was down here. So, things were getting almost like 8, 9 feet high. And so our client that we're working with didn't want to have to, it has large maintenance costs having to reshape that after a large storm event. Eventually got it down to the orange here, which is a little bit smaller, kind of helping that. You might look and say, well, this gray one's even lower, but this one was actually a failure that you see here. Now, one of the things that the physical model study was able to help look at was ensure that the cobble material would not get transported onto the roadway during a large wave event. So this photo here, as you see all this cobble material that got transported over those blocks and away from the shoreline, that matched up with this gray one here. So it looks good, but actually didn't perform very well. And I should note that these cobble materials, and they scale in the real world to 3 to 9 inch cobble. So you can imagine you don't want these things getting flung around during a large storm event. My last example here is using physical modeling as a tool to de-risk is for a living dike in Boundary Bay, BC. Now, I recognize this isn't a Great Lakes application, but you'll see why I wanted to include this study in a few slides from now. But essentially, the purpose of this project, the living dike itself, is to implement small-scale or experimental pilot projects to gather information on current knowledge gaps to determine the most appropriate methods to build a salt marsh and a living dike in Boundary Bay. So Boundary Bay is located in the city of Surrey. So you can see there's Vancouver here, and Boundary Bay is just below it. Boundary Bay, it's expected to have, a high flood risk by the year 2100 due to relative sea level rise. Where you can see here's the outline of the shoreline in present day, and here's, the various flood risk metrics for the year 2100 for the whole area. And so the city of Surrey wants to construct a living dike around the entire bay. What a living dike is, it's kind of a gray-green approach. You still do have a classic kind of dike, which is illustrated here. However, immediately offshore of the dike in the nearshore region, you install the salt marsh. And the idea is that the vegetation of salt marsh will attenuate the wave energy and reduce the wave heights. So when the waves actually get to the shoreline and interact with the dike, a lot less wave energy there. And so you can get away with having a lower dike crest elevation, less material, and kind of better access to the water line. Now, the thing with these salt marshes, as when you don't want to plant all this nice new vegetation, have a large storm come in, and then wipe it all away before that vegetation can get itself established and matured. And so you want to put in an edge stabilization measure at the offshore edge of it. You want to put in some sort of structure that will both attenuate wave energy and kind of retain that sediment that you placed with the vegetation from migrating offshore. And so what we helped them do was do full-scale and half-scale physical modeling experiments to inform the design of 4 different edge stabilization measures prior to the actual pilot project construction in Boundary Bay. So we tested these 4 kind of features were a natural sand berm. So just, this is looking towards the shore from the offshore direction. It's just a slope up to the salt marsh here. One thing I should note that we didn't actually model the vegetation. We just looked at the sediment that would be placed in order to facilitate the growth of the salt marsh. And then we figure if that remains relatively stable, then the vegetation will have, a good chance of becoming established. So we did a natural sand berm at full scale, a rounded gravel berm at full scale, a berm consisting of oyster shell filled bags, so empty oyster shells placed in bags. And then the brushwood dam was done at half scale, mainly due to just height restrictions in the flume. And the brushwood dam itself is just, these vertical wooden posts with some bundles of brushwood or sticks in between them that are fastened down over top with some biodegradable rope to hold it all down. So the study investigated the stability, wave attenuation properties, and the salt marsh platform with no vegetation, and the morphologic change to the salt marsh platform. Again, not going to get into the details of the study. There's a paper you can with the details up here that kind of have a better look at into the study results. But we essentially looked at wave attenuation results. So this is going from offshore to onshore for the 4 different edge treatment features, as well as the salt marsh platform change results. So this is elevation for the 4 different features and the 4 colored lines as you move kind of towards the land here. And just some photos of, before and after the large wave events that we tested. You can see a scour hole developing on the downwave side of the oyster shell berm here, some scour around the brushwood dam, And this is a video of some large waves interacting with the rubble mound structure. So you can see them breaking over top. All this darkened area that you see down here, that's all sand being entrapped and kind of entrained in the water column due to the breaking waves and transporting that sand. Here's some nice photos of these things actually installed in Boundary Bay. So again, this was just the pilot project. So they had you can see a couple different plots where they had the different edge treatment feature and some different vegetation growing within them. There's the brushwood dam, the oyster shell filled bags, the rubble mound structure. I don't have a photo of the sand berm because that one's kind of hard to distinguish by eye. And you can kind of see, this was shortly after construction, so you can see all the vegetation kind of planted in its early stages. Now, I spent the last, about half an hour talking about how great physical modeling is, but even a full-scale physical model is still a model. So there's a number of processes that can't be represented either feasibly or easily in a physical model. And, Mother Nature can be cruel at times. And so through this pilot project, it showed, gave great information on how these various kind of edge treatment features and salt marsh planting and stuff reacted under, real world conditions. So one thing that was found was during winter, ice would freeze up in the bay during the colder days in Vancouver or near Vancouver. And then the tide would come in and actually lift that light ice up. And that ice would take all that nicely planted vegetation with it. So that removed a lot of the vegetation within the pilot study. And then just recently, a few weeks ago, um, project partners went out to look at the site and noticed this is a very large tree with a big root wad. You can kind of see that tree again down here. That just came through and destroyed a lot of the oyster shell bags, cutting them open. You can see the oyster shells dispersed all amongst the plot here. Not too much vegetation really around. You can see little plugs of it around. And then also the brushwood dam. Originally, this was all nice and filled with those bundles of sticks, but I guess the rope that was holding them down got severed either by a large storm or maybe some driftwood. Cut that rope as the tide comes in, lift all that brushwood out, and now you're just left with these vertical posts. So the study's still ongoing. The rubble mound structure, so that rounded gravel berm, is still holding strong, and actually just the natural sand edge is still performing well with limited kind of reshaping of it. So, the study's underway, but it shows the importance of pilot projects and that, physical modeling can only get you so far. At some point, you need to build it in the real world and expose it to the conditions. In conclusion, physical modeling can be a useful tool to learn more about nature-based solutions before implementation. It can be used to help optimize the design to reduce costs or investigate methods to minimize potential maintenance. However, as I just discussed, all models need to make assumptions and simplifications. Therefore, there's still a big need for pilot projects and field implementations in order to investigate how nature-based solutions can perform under real-world conditions. And the exciting part is still lots to learn in the world of coastal nature-based solutions, and it's a fun kind of work to be around and to be able to participate in. Thank you everyone for your time. I've left my email here if anyone wants to send me an email with any questions they may not want to ask in the chat, but I'd be happy to answer any questions now.
Great. Thanks so much, Mitch. You were able to share a lot of information in a relatively short amount of time, so I really appreciate that. I do see a few questions in the chat, so I'll just go in order here. So the first one says, during modeling with vegetation, you mentioned two densities, low and high. Is the vegetation density ever low too high in the same test to simulate more of a vegetation gradient?
No, we didn't test that in our test. It was the same density throughout the whole kind of reach, mainly because we had a limited length that we could do the salt marsh in. And so there just wasn't enough space to kind of provide a transition from a lower to higher density. I should say that further studies are being conducted at INRS by Jacob Stoley and his students there, where they have a larger flume and they're looking at a lot more variation in vegetation density and things like that. So that work's currently underway.
Great. So the next question here is, how were the grain size for the mobile beach scaled? Using what number and to wave heights, or how were the beach grain sizes scaled?
Yeah, so scaling mobile bed material, so sand, is difficult in physical modeling. It's a challenging thing to do, mainly because you can't just scale it based on fluid scaling, based on the diameter, the grain size diameter, because you'll end up being in kind of this clay and silty domain for most appropriate model scales. And then you end up with all issues with cohesion and that sort of stuff. And so what we actually scale is the settling velocity of the sand itself using fluid scaling. And so the idea is that a beach material in a coastal region gets transported mainly um, through suspended sediment load as opposed to bed load. And so if you're able to scale the settling velocity of that sand, it gives you a reasonable representation of how that material would actually move in the real world.
Great. And then that same person asked if you could provide the paper that you were referencing during that slide, I'm guessing on the grain size or the scaling, because they say it's hard to sometimes get those papers.
Yeah, they certainly can be. My email's up there. Feel free to send me an email and I'd be happy to send along any papers that you'd be interested in reading.
Perfect. Okay, so I hope that answered the question, Roger. I'm going to move on to the next one. So, what was the cost to complete a model like the Mississauga one, and how did you save on EA process? How long does it take to get in a queue for a facility capable of doing this work? So, kind of two there.
Yeah, so the model cost, I can say that Mississauga one was I think it was about 8 years ago or so now. And as everything else, costs have changed. At the time, the cost to do that model was I think it was about 250,000 for that model. And then it saved over 3 million on the EA based on the EA cost. How did it save? I believe it was mainly on the reduction in crest elevations of those rubble mound structures. So being able to reduce the amount of material needed to construct those structures was able to reduce the costs. I believe it's outlined a bit more in that conference paper I referenced. So again, if you send me an email, I'd be happy to send it along to you, as I believe the optimizations achieved through the physical model are outlined in a bit more detail in that paper. And then, sorry, the third part, how long does it take to get in the queue? Honestly, it really depends. Lately we've been quite busy here, and so you'd have to expect to wait probably about 6 to 8 months to get in the queue. But depending on the model and the size of model and our current schedule, we've done everything from almost start the next day to having to plan 6 months out. I would recommend kind of the larger the project, like that Mississauga one. It's best to get in touch with us as early as possible so we can kind of be able to get the project slotted in our facility queue here.
Perfect. And then kind of a follow-up to those first two questions. Have you run 3D computer modeling to compare the results of the physical modeling?
We have. Typically for the projects that we work on, we work with a design consultant or a coastal engineering consultant, and they typically do their own numerical modeling studies. So what they'll do is run some numerical modeling studies to come up with their kind of preferred design. We then test them in the physical model and provide all that data and measured data back to them. And then sometimes, depending on the project, the consultant will then, rerun some numerical simulations using kind of some of that physical modeling data to further calibrate and validate the numerical models. We've here at the NRC, we've started looking at CFD modeling and how it compares to some of our physical modeling results. And it really depends on the phenomena that's being studied. Things like wave interactions and wave attenuation is something that numerical models can do well. But if you're looking at sediment transport or stability of rubble mound structures, that's something even quite advanced CFD models can still struggle with.
Great. Okay, we have another question here. When you build a model of a basin, can you change wave directions in order to study different storms and long-term behavior?
Yeah, so in the basin, our wave machines in the basin are actually called, I didn't get into this portion of it, are called multi-directional wave machines. And so you can generally create waves plus or minus 40 degrees off of normal from the waveboard. So plus or minus 40 degrees from other directions. So with the same model set up, without having to reorient anything, we can test multiple storm directions. Long-term behavior is difficult to do in a physical model, mainly because when we run the tests, they're done at a static water level. and with, one type of wave condition. And then we change the water levels, or subsequently change the water levels and the wave conditions. But to do something long term, you really need to have lots of periods of calm with some big storms mixed in. And so it gets a bit tricky to do in a physical model. That's why those pilot projects are kind of, and for especially for nature-based solutions, pilot projects are kind of a really needed thing as they allow for that kind of more long-term behavior to be studied.
Great, thanks for that one. I do see another question in the chat here. So in the case of your last example, was anything revised to mitigate the issue of the moving ice uprooting that vegetation?
Nothing has been revised yet. The city of Surrey is letting the pilot project kind of run its course. I forget the timeline they had in mind, but they had a certain length of time. They wanted to kind of let that run its course. And then they'll take the results from that and I think go back to the drawing board a little bit before they do kind of a wider implementation of this living dike kind of solution.
Great. Were there any other questions from the audience right now for Mitch? I can ask one while we wait in the meantime.
Sure.
You really briefly mentioned at the beginning of your talk about how you can scale these physical models. Would you be able to, go over that or expand a little bit more?
Yep. Yeah, I've got maybe I'll share my screen again. It'll probably be easier. I didn't include this slide out of time. But the big thing for scaling a physical model is to establish similitude between the model and the real world. And there's kind of three types of similitude that need to be kept in mind. There's geometric, which is basically the dimensions, the length, width, and height of the object that you're trying to model. There's kinematic, which incorporates velocities and accelerations. And there's dynamic, which is the pressure, inertia, and gravity. So I say that almost all hydraulic physical models use the similitude of the Froude number. The Froude number on the top right here being the relationship between the inertial force and the gravitational force. And this is mainly since the fluid motion and fluid structure interactions are governed by a balance between gravitational and inertial forces acting on a water particle. So essentially, if your Froude number is the same in the real world as it is in your model, you can ensure that the interactions of, for example, a wave with a rock is kind of similar between the real world and the model. Now, since all physical models use water because it's just not feasible to use a different fluid in the quantities that we require it, you can't keep the Froude number and the Reynolds number the same when you're doing a scaled model. And just a reminder for anyone, the Reynolds number is the relationship between the inertial force and the viscous force. So where the Froude number is inertial and gravitational, Reynolds number inertial and viscous. And since water is used in full scale and used in the model, obviously you can't scale this viscous force. And so it's important to keep the model scale as large as possible. So, in the order of 1 to 20, 1 to 30, as opposed to 1 in 100, because that keeps the Reynolds number as large as possible in the fully rough turbulent regime, and then it mitigates the scale effects. If you have your model too small, so if the model scale is too small, you can get into issues with viscous forces, with surface tension and things like that, especially when you're looking at waves breaking. If you have too much surface tension in your model, your waves just won't break properly, and it'll be hard to generate those kind of small waves as well. And so the larger model scale is always the better to be able to keep that Reynolds number high.
Great, thank you. I do have another question here for you. What was the timeline for the pilot study in BC? Is this the last step in modeling before broader implementation, or will there be iterative numerical or physical modeling after that pilot?
Yeah, so what happened was we did the physical model in the summer of 2022. Yeah, summer of 2022. It was constructed shortly after, I believe. And then it's been now left for about 2 years now. And then during that time, a PhD student and Professor Ryan Mulligan at Queen's University have been conducting some Delft 3D numerical modeling of that same site. And then Professor Ryan Mulligan also has a master's student now who's just starting up to do some additional modeling to kind of help with that kind of more larger implementation within Boundary Bay. And then the city of Surrey will have their own kind of decision making to do on how much they can do at this stage and how they want to approach it. But those kind of next steps are starting to being looked into now.
Great. Do we have any other questions from the audience here? I know you went through a lot of questions there, Mitch, so I appreciate you taking the time to answer those. I do see one coming in. They might have missed it, but can you please elaborate more on the downscaling method, distorted method included?
So we scale based on the Froude number. For coastal modeling, it's always undistorted. I think that's what your question's getting at. So an undistorted model means that the lengths and the depths or the elevations are all modeled or all scaled based on the same factor. Whereas distorted model, which is sometimes used in river model studies, since rivers are very wide and relatively shallow, sometimes they have an undistorted model scaling where the widths are at a different scale factor than the depths or the elevations. But yeah, we scale based on the Froude number, and for coastal modeling, it's almost always an undistorted model. So the elevations and the widths are based on the same scale factor.
Great. Okay, do we have any other questions from the chat? I know this has been a really great dialogue and conversation back and forth. So Mitch, I appreciate you taking the time to answer all of these questions and to share as much information as you did in such a short amount of time. Okay, I see another question here. Would you please summarize a list of information needs to inform the model? I may have missed it.
Yeah, so information used to the model. A big thing is the bathymetry. You need accurate bathymetry data because that's what controls the wave transformations as they transform from deeper offshore waters to the nearshore region. You need information. It depends on the type of model. If you're looking at like a coastal structure, you need information on the structure itself, including armor stone sizes, cross-sectional designs, elevations, all that sort of stuff. And then kind of obviously another big one is the wave information itself. So which water levels and waves that want to be tested in the model. All that information combined allows us to choose an appropriate scale and facility for the model. And then we can always go from there. But those are kind of the three big ones.
Great. I hope that answered your question there, Greg. Yeah, and Mitch, you said you were going to be at Coastal Zone Conference, I believe, in PI next year, right?
Yes. Yep.
Great.
I'll be at the Coastal Zone Canada Conference at PI. I'll be presenting, hopefully, I submitted my abstract, hopefully it gets accepted. But I'll be presenting on some design equations that we developed for oyster shell filled bags. So these are being used to protect shorelines, but there's no design criteria out there for them. And so through the physical modeling studies, we actually propose some design equations that can be used to estimate the wave attenuation and stability of these oyster shell filled bags.
Great.
So
Well,
hope to see
that's
many
really
people.
exciting.
Yeah, hopefully see a lot of you there.
Yeah, do let us know if anyone here is able to attend that Coastal Zone Conference. It'd be great to meet up with some of the community of practice members. If we don't have any additional questions for Mitch, then I think that may wrap up this webinar. Again, it will be posted on the YouTube page if you want to revisit it. And you have Mitch's email there if you end up having additional questions later in the week and just want to pick his brain more about some of this physical modeling. So with that, thank you so much, Mitch, for the presentation. Thank you for everyone who was able to attend. Look out on our LinkedIn for the next webinar coming up next year at some point. Thanks a lot, everyone. Talk soon. Bye-bye.
Thanks, everyone.